Yes. Now, so welcome to the class. Today, we want to look at subgroups. We've been looking at groups and now want to look at subgroups. Of course, what we know is that if you're given a set, or a group is a set together with operations, could be addition or multiplication. Now, we know that every set has a subset. So, but not all subsets will form subgroups. Not all subsets of the set would form subgroups. So we'll, in this class, we will want to know what are the subgroups of, if you're given a group, how do you get subgroups? That is what we'll be doing. That's what we'll be doing. Of course, a subgroup is just, is a subset of a group, and it must fulfill the axioms that a group fulfills under the same operation of the group. What this means is that if the group is additive, then the subgroup will also be additive. If the group is multiplicative, then the subgroups will also be multiplicative. And the subgroups must fulfill the axioms of the group. But normally we try and just use like 3 axioms that if we are testing a subgroup, we just test for 3 axioms. And if they are satisfied, then that is okay. And that, of course, what we'll also be looking at. So the definition, a subgroup must be non-empty. That means it must have elements. It's a group had elements. And so the subgroup must also have some elements. And then it must form a group. A subgroup must form a group. That's what I've been saying, that it must fulfill the axioms of the group. So that's what we mean by it must form a group under the same operation as the group. So if you took a subgroup and tested for a group, it must qualify to be a group. That's what it means. Now, the notation that we use, if H is a subgroup of G, then this is the notation. So if you see this notation, it means subgroup. So we'll not be using it to mean less than or equal to. As far as groups and subgroups are concerned, this notation would mean subgroup. And so I would read this as H is a subgroup of G. That's how we would then read this, but not that it's less than or equal to. It's a subgroup of G. Now, so we have subgroups. We have 3 categories, and of course, I'll be looking at that. I want to begin by looking at this, the proper subgroup, and I've defined it. I've said that if H is a subgroup of G that is not equal to G and is not equal to the empty set, the set comprising of the identity, then this H shall be called a proper subgroup. It's a proper subgroup. So what we're just saying is, for instance, supposing a group had, like, let me say 10 elements. And then its subgroup would have 9 elements. Between 2 and 9, we'll have between 2 and 9 elements. That's what this means. So it should not have the identity only. It should not have the identity, and it should not be equal to. If it's not the identity, if it's not equal to the identity and it's not equal to the entire group, then we call it a proper subgroup. And if it's a proper subgroup, if you are sure it's a proper subgroup, then you can use this notation. It means the same thing actually. How do I read this? I read this as H is a subgroup of G. H is a subgroup of G. But then I understand that this H is a proper subgroup. I understand it that way. If I see this symbol, that's how I understand it. That it's a proper subgroup. In other words, it's not equal to G. And again, it's not equal to the group, a subgroup comprising of the identity element E. Now, I had already said that a subgroup must fulfill the axioms a group fulfills. But again, I already also said when you were starting that instead of going through all the axioms, we just come to 3 axioms. And once we see that those 3 axioms are fulfilled, then we can declare it a subgroup. And the first axiom that we will be looking at, of course, when we say non-empty, non-empty, it must be there. It means it must have elements. And then the first axiom we'll bring looking at is closure. That if you pick any 2 elements inside this subgroup and multiply them, that is, if the group is multiplicative, or add them. So I'm using this symbol. You can add them if the group is additive. Then the result must be in that set. And the other axiom we shall be looking at is the existence of the inverse. That every element in that subset should have inverses. And then the last one is that the identity element must be there. So if the identity element is there, and then every element has an inverse, then there's closure. These 3 are enough to declare it a subgroup. So if you check these 3 and you find that they're all satisfied, then you can confidently say that it's a subgroup. Now, I had already mentioned this, that we have 3 classes of subgroups. The first class is the trivial subgroup. This is a subgroup comprising of only the identity element. This subgroup is the trivial subgroup. The subgroup comprising of only the identity element. What I mean is under addition, this is the trivial subgroup. Under addition. Under multiplication, this is the trivial subgroup. Under multiplication. Because these are the identity elements. This is the identity element under addition, and this is the identity element under multiplication. And so I used E as a general identity element when I do not want to either talk of additive or talk of multiplicative groups, then I can use the general identity element. Now this subgroup is the trivial subgroup. You can test and see that it's closed under addition. It's also closed under multiplication. And you can also see that the identity element is there. And you can see that every element has an inverse. Let me just explain that. Under addition, the inverse of 1 is 1. Because when you multiply them, you get the identity. That is under multiplication. Under multiplication, the inverse of 1 is 1. Under addition, the inverse of 0 is 0. So this is a subgroup. It fulfills the 3 axioms. Closure is satisfied because E plus E will be E. I mean 0 plus 0 will be 0. That is under addition. Under multiplication, E times E will be E. Under multiplication, now you know that I'm referring to 1. 1 times 1 is 1. Under multiplication. Now, so we've seen the first category of subgroup is what we call the trivial subgroup. That is a subgroup comprising of the identity element only. And again, just to emphasize that the identity element is a subgroup of every group. Of course, we'll be looking at subgroups of a group. Subgroups of a group. The first subgroup of any group is the subgroup comprising of the identity element. The other class of groups is what we talked about, the proper subgroup, then the entire group. So that is a proper subgroup. And we'll be looking at examples, of course, then you'll get to know these definitions. It must be smaller than the whole group, the proper. But again, it's not equal to the trivial. It's not equal to the trivial. It must be bigger than the trivial. And then we have the improper subgroup, which we also call a whole group. A whole group is the improper. That is the entire group. The entire group. For instance, if we are talking about if the group is Z6, this Z6 has subgroups, but itself is a group, is a subgroup. Itself is a subgroup. Every group is a subgroup of itself. Now, this subgroup, therefore, is the improper subgroup. Improper subgroup. So we now have the trivial subgroup, we have the proper subgroup, and then we have the improper subgroup. And those terminologies, I think they're important for us. This point I've already said. I've said that if you are to list the subgroups of any group, then this subgroup comprising of the identity element will always be a subgroup. That's what I've said, that the subset, this subset, consisting of the identity element alone is always a subgroup of any group. And the other obvious subgroup is that the entire group is a subgroup of itself. And that we already mentioned. And then we would have other subgroups which we shall call the proper. So what I mean is, supposing somebody was to ask you to give the subgroups of Z6, then I would say the first subgroup I will go for is the one comprising of the identity element. The other subgroup is the group itself. The group itself. Then we have other subgroups, the proper subgroups. And so our interest therefore will be knowing how to get the proper subgroups. But these others are obvious. These others, the one comprising of the identity and the group itself, those are obvious subgroups. If I look at how to obtain subgroups, I want to look at examples of subgroups. Now, I've said that the set of integers is a group of all integers and addition. What are its subgroups? We have its subgroups. For instance, we can talk of the set of even numbers, the set of even numbers. You see, this means, you see, if you have, these are integers, and the integers we have are -4, -2, no, -3, -2, 0, 1, and so on. Now, I've just multiplied 2 by this, and I've called them the set of integers. No, even numbers. So when you multiply 2 by this, what you get, and I want to show you that they're even numbers. 2 by that, you'll have -8. 2 by that, you have -6. 2 by that, you have -4. 2 by that, you have -2. 2 by that, you have 0. Then 1, no, 2. Then 4, and so on. So this is a set of even numbers. It's a subgroup of the integers. It's a subgroup of the integers. This is not the only subgroup of the integers. If I took the integers and multiplied them by any other number apart from 2, I've just multiplied them by 2. I can also multiply them by 3 and still get another subgroup. I can even multiply them by 20 and get another subgroup. I can even multiply them by 7,020. Any number. Multiply the integers by any number. What you get is another subgroup of the integers. So that is the first example. And of course, when you are looking at groups, we say that integers were groups and addition. So that means, again, the subgroups will be subgroups and addition. That is why you can see a plus sign here. Of course, that plus sign is not important because we already know that integers are groups and addition. So that means, again, the subgroups will also be integers, it will be subgroups and addition. Now, so I've said this statement here, I was just trying to prove that it's a subgroup. Just a minute. So I was just trying to prove that it's a subgroup. So I was saying that closure is satisfied. That's what it means. Closure is satisfied. So if you took any two numbers from here, X and Y, and of course, these are the numbers we're talking about. I talked of -8, -6, -4, -2, 0, 2, and so on. If you take any two numbers here and add, the result will be a member of this set. That is what this statement means. Pick any two members and add the result to a member of this set. And you can see that the inverse of every number exists. The inverse of 2, of course, is -2. The inverse of 3 will be -3. The inverse of -6 will be 6, and so on. So every element has an inverse. And you can see the identity element is there. The identity element is there. So it means it's a subgroup. So this part, I was just trying to prove that, of course, it is a subgroup. I was trying to show that 2Z is a subgroup. I've already explained this part. I've already said that 2 can be replaced by any other number, and replaced by 3, can be replaced by 4, or even 10,000. Now, the other examples of subgroups are these. Of course, I began by saying that these are groups, as we had already said, these are group, these are group, these are group, these are group. But of course, when you look at them, the complex numbers are more than these. So these ones, the real numbers are contained in the complex numbers. So the real numbers, of course, will then form a subgroup of the complex numbers. And then the rational, these are the rational numbers. Rational numbers. Rational numbers are any number which can be written in the form A out of B, where B is not equal to 0. Any number that can be written in this form, like 2 out of 5, like 1 out of 3, like 4, because 4 can be written like that. So it's a rational number. All the whole numbers you know, all the fractions you know, are rational numbers. And so that's why they are contained in the real numbers. So there are subgroups of the real numbers. Then these ones are less. So there are subgroups of the rational numbers. And then the even numbers. So that is why I arranged them this way. I said that the complex numbers are more. So these even numbers are subgroups of the integers, and the integers are subgroups of the rational numbers, and the rational numbers are subgroups of the real numbers, and the real numbers are subgroups of the complex numbers. So of course, then these are subgroups. Those are examples of subgroups. You can see that each of these is a subgroup of another one. Apart from the complex numbers, all the rest are subgroups of another set or another group. Then we come to what we are used to, the integers mod n. Integers mod n. So I took one example where n is 6, and I was trying to find out what are the subgroups of this. And this is what we'll be measuring on. We'll be measuring on identifying subgroups. So I just identify one of the subgroups. And I said the subset this forms a proper subgroup of this under addition. I don't want to emphasize on how I got this because I'll be showing examples. I'll be showing examples of how to get subgroups from this part, from this subgroups of this. Now, this is a subgroup. What I was emphasizing is, can you show that this is a subgroup? To show this as a subgroup, one, you show closure. You can see I've shown closure. Pick 2 elements, added, and the result is a member of H. And then, can you show that the identity element exists? And that's what I've shown. Now, so the other part that we're supposed to show that every element has an inverse. For instance, you can see the inverse of 2 is 4. Because 2 plus 4 gives us the identity 0. And the inverse of 4 is also 2. So these elements are inverses of each other. Okay, so let's look at another example of subgroup. Now, I've taken this example. These are complex numbers under multiplication. And then I claim that this is a subgroup of this because they are complex numbers. These are also complex numbers. They form subgroups of this. And you can show that they form subgroups. I'd said we can see that in example 56, of course, but the example 56, I've done it. But of course, before we reach there, we can see that there's identity element. The identity element is there. So we are proving that it's a subgroup. You can see the identity element. You can see that the closure is there. You pick any 2 elements. Like if I take 1 times -1, I get -1, and -1 is a member of this set. So closure is satisfied. You can even pick another element like 1 times I. You get I, and I is a member of this set, and so on. And you can see every element has an inverse. For instance, the inverse of 1 is 1. because the product gives us 1. The inverse of -1 is -1 because the product gives us 1. The inverse of I is I. Now it's -I. So that gives us 1. I think that is true because what we know is that the square root of -1 is I. So when you square on the right of both sides, you have the -1 is I square. So if you have I times -I, what you get is -I square, which is negative, but I square is -1. So this gives us 1. That gives us 1. Now, we also have matrices. These matrices, again, we are seeing that if you have matrices of complex numbers, and then these are real numbers, and then these are rational numbers, and these are integers, then this matrix will be a subgroup of this, and this will be a subgroup of that, and this will be a subgroup of that, just as we had done earlier with the numbers. So if you have matrices again, we have those ones being subgroups of each other in that order. Now, number F, this is another type of matrix. Is another type of matrix, and is a matrix where is a square matrix, n by n, the square matrix, which is invertible. Which is invertible, and also determinant is 1. So any matrix that has an inverse and has a determinant of 1, this is how we denote it. Now, so this is a subgroup of this. That's a subgroup of that. Now, I think that is enough with the examples of subgroups. There are so many examples. Now, I've noted that if you take 2 subgroups and get the intersection, the answer you get to the subgroup. Just to remind us what intersection is. Supposing I have these elements, let me use A. Supposing A is the subgroup comprising of 0, 1, 2, and 3. And let me say that I'm just giving an example. In fact, I just want to define intersection. And suppose I have another set comprising of 2, 7, and 8. What we mean by intersection of A and B is the elements common to the 2 sets. Elements common to the 2 sets. That's what we mean by intersection. The elements common. Where do they intersect? Where do they intersect? So if this is a set and this is another set, the intersection is this. This is the area that is common to both of them. That's what I mean by intersection. So what I'm then saying is that if you have 2 subgroups of a group, of the same group, subgroups of the same group, and get the intersection, that intersection will also be a subgroup. Maybe we'll look at an example later. Now, this definition is now obvious to us. When we talk of order, we mean the number of elements. So the order of a subgroup means the number of elements in the subgroup. And this is how we denote it. The number of elements in H is denoted like this. And what Lagrange theorem says is that the order of a subgroup will always divide the order of a group. The order of a subgroup will always divide the order of a group. Let me give you an example just to illustrate this. Supposing the order of the group is 12, then we expect the subgroups of this group. We expect the subgroups of this group to have orders which can divide this number. So we expect one subgroup to have order 1, because 1 can divide this number. We expect a subgroup to have order 2, because 2 can divide this number. We expect order 3, expect order 4, order 6, then order 12. We expect subgroups of this group to have any of these orders. That is what Lagrange's theorem says, that the order of a subgroup would always divide the order of a group. So you cannot have the order of a group, subgroup not dividing the order of a group. That is not possible. Let's now go to examples before we just look at the code that will be giving us subgroups. Now I want to begin by looking at subgroups of integers mod n. And I began by stating that for us to understand how to get subgroups here, we need first of all to understand that these subgroups, the subgroups that we are looking for, will be cyclic subgroups generated by the divisors of n. And I underline the word divisors of n. And so we know what a divisor of n is. So supposing n is 6, the divisors of 6 will be 1, 2, 3, and 6. That's what I mean by divisors. And so I've said each of these divisors of n would have a corresponding subgroup. Would have a corresponding subgroup. Of course, it will be cyclic, but they will be so we can know how many subgroups we are looking for in this Z4. Of course, some subgroups may be the same. So when we are the same, we just pick one. But what we know, Z4, the numbers can divide 4, divisors of 4. Divisors of 4 are 1, 2, and 4 itself. And I've already said here, each of these divisors would have a corresponding subgroup. The question was, find the subgroups of this. Of course, it was proper. The question is proper, but I'll not answer the proper, but I'll answer the entire subgroups, all the subgroups. Then, of course, we will pick out the ones which are proper. So the divisors of 4 are this. Each of these divisors will give us a subgroup. That's what I said here. Each of these divisors will give us a subgroup. And that subgroup will be cyclic. What cyclic means is that we will have a generator for those that will be generating those subgroups. There will be a generator. And of course, when I'm writing the code, I'm using that word generator. Using the word generator. So in my code, how do I get a generator? Devices are these. Now the generator for one, the generator corresponding to one would be n divided by 1. So the generator will be 4. The generator will be 4. So I'll add 4 several times until I get the identity element. And I can see if I just add the 4 once, I already have the identity element. So that means what is the subgroup of generated? 4 has generated this subgroup. 4 has generated this subgroup. And that's what you see here. 4 has generated this subgroup. Now, what is the generator corresponding to 2? It will be 4 divided by 2, which is 2. So in other words, I added 2 several times until I get the identity. That's what you mean by cycling. So 2 once will be 2. 2 twice will be 4, but 4 is 0. So what I've generated, therefore, is 2, 0. That's what you can see here. That 2 has generated this subgroup. So the first subgroup we've looked at, this is what we call the trivial subgroup. This is the trivial subgroup, the subgroup comprising of the identity element. Now we have this other element 4. The generator corresponding to that will be 4 out of 4, which is 1. That is the generator. So I add 1 several times. 1 once will be this. 1 twice will give us 2. So until you get the identity, 1 3 times gives us 3. 1 4 times gives us the identity. So what have we generated? We generated this 1, this 2, this 3, and that is 0. So this is what we've generated. So 1 has generated this 0, 1, 2, 3. Now we've considered all the divisors. None of them is left. So once you consider all the divisors, it means you have all the subgroups required. So this group here has 3 subgroups. And the subgroups are what we have here. You have this subgroup comprising of the identity, you have this subgroup, and you have this subgroup. Now the question was, give the proper subgroup. The proper subgroup from our definition, and let's go back to the definition just to understand it. By definition, the proper subgroup is that which is not equal to the entire group and is not equal to the trivial subgroup. So the proper one is this. This is the proper one. But you can see this one equals the entire group. This one equals the entire group because the entire group Z4 is just 0, 1, 2, 3. So you can see this subgroup here is equal to this group. So this is what we call the improper subgroup. Improper. And this one we call it trivial subgroup. And the other subgroup, which was smaller than the proper one and not equal to this one, is what we call the proper subgroup. That's how we call them. And that is what I've just explained here. That's what I explained in the continuation of this proof. Now, I just want to look at another example so that the point sinks home. how do we get subgroups of Z12? To get subgroup of Z12, first of all, we identify the divisors of 12. The divisors of 12 are these: 1, 2, 3, 4, 6, and 12. Then look for the generators corresponding to these elements. And how we look at the generators is to take 12 and divide by 1. So 12 will generate. So if I take 12 and divide by 1, I have 12. So 12 becomes a generator. I want to see what 12 will generate. So I add 12 to itself until I get the identity. So if I just add 12 once, I already have the identity. So if you look at the bottom, you can see what I've written, that 12 generates the trivial subgroup. The trivial subgroup. Then the other generator will be 12 divided by 2, which is 6. And so I add 6 to itself once, it will be 6. Then 6 to itself twice, it will be 0. So what is generated is 0, 6. These are the elements generated. So that is what you can see there. The other generator is 12 divided by 3, which is 4. So I add 4 to itself several times. 4 once will be 4. 4 twice will be 8. And 4 thrice will be 0. And so you can see that 4 generated that subgroup. So I've already obtained the subgroup, the trivial subgroup. And then this will be proper. This will be another proper because it's smaller than the entire group. The other generator will be 12 divided by 4, which is 3. 3 to itself once will be 3. Twice will be 6. Thrice will be 9. And then 4 times will be 0. The other generator will be 2. That is 12 divided by 6 will be 2. 2 itself once will be 2. Twice will be 4. Thrice will be 6. 4 times will be 8. 5 times will be 10. Then 6 times will be 0. Again, this is a proper subgroup. This is a proper subgroup. The other generator will be 12 divided by 12, which is 1. So once will be 1, twice, thrice, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10 times, 11 times, and then 12 times. The last one there is the improper subgroup. This one is the improper subgroup. The one which equals the entire group. Because the entire group Z12 has these elements 0, 1, 2, 3 up to 11. So that is the improper subgroup. But the rest are proper apart from the last one generated by 12, which is trivial. So I think when we are looking at an additive group, it's very easy for us to get the subgroups. It's very easy for us to get the subgroups, especially using the knowledge, the idea of generators. So I use that concept to come up with the Rust code for getting generators and getting subgroups of an additive group. So I've said this Rust program generates and prints all subgroups of an additive group Zn. So we'll be using the same tactics. And look what the program, just the same tactics we've been using. The first tactic was to find the divisors of n, and then generate the subgroups, And how are we doing? We're getting the divisor, first of all. We're getting generators. We're getting generators. And then after getting generators, we'll then get the subgroup. So you can see this part is to get generators. And then we have, no. This one is to generate the subgroup. Generate the subgroup. And this one is to generate to get the generators. To get the generators. So let me now show you how it works. Then we have this main function. Of the main function, supposing I want to get the subgroups from Z24, I would input my 24 there. Of course, you can replace it. And then this main calls for generate all subgroups. Generate all subgroups. Generate all subgroups is here. Generate all subgroups is here. And then it will then print subgroups. Then we have here this part for subgroup. In subgroups, let mute this vector and then subgroup vector sort and stable, then print subgroup. So I'll explain what those means. But the thing is, first of all, it calls for this generate all subgroups. Generate all subgroups is here. What this one does, it begins by creating an empty vector and saying, let mute subgroups. So that means we are letting the subgroups be this empty vector. So this is where the subgroups will be stored. The subgroups will be stored here. That's why we'll be storing the subgroups. But it's mutable. That means we begin when it's empty, then at some point we get a subgroup we store there, then we get another subgroup we store there, and so on. So it just has this one, but it's not calculating the subgroups. What will be calculating the subgroups is this part. So after creating this empty vector, then it goes to find the divisor, the generators. Then it says for D in the divisors. You see the divisors is up here. We have what is doing the divisors. So it's calling for the divisors function. So the divisors, of course, the divisors will be getting the divisor. If you have 12, no, you're talking about, was it 24? This one is supposed to get all the divisors of 24. 1, 2, 3, and so on up to 24. So there's this empty vector. There's this empty vector. Then it goes I between 1 and 23. Because n is 24. So it goes 1 to 24 minus 1. So in that range, how is it getting the divisors? How is this part getting the divisors? So in the range that it begins by creating an empty vector called divisors, an empty vector called divisors. That's why we'll be storing the divisors. And it's mutable, begins empty, but then with the time, it's filled. Now look what it does. In the range up to 23, that is 24 minus 1, 24, which is 23. That range, if this is I, these are the I's. So for every I in this range, if n, which is 24, divided by I gives a remainder of 0, then it means that I is a divisor. It's then pushed inside that vector. So for instance, it begins by I is 1. So it checks 24 divided by 1. It wants to see whether the result is 0. If 24 divided by 1, the remainder is 0, then 1 is a divisor and therefore pushed inside there. Then it goes the next I, because it's moving I from 1 to n minus 1. So then now considers 2. If n divided by 2 leaves a remainder of 0, then 2 is a divisor and is pushed there. Then it goes to the next I, which is 3. Then it considers 24 divided by 3. If the remainder again is 0, 3 is pushed there. It does that up to 5, but 5 will not be pushed. Then 6 will be pushed, 7 will not be pushed, and so on. 24 itself will be pushed. So then it has the divisors. It has the divisors. So let's go back to where we came from before we came to this. So we've already explained how the function for divisors will be working. You have the elements and it's just moving from 1 to n and checking whether the elements from 1 to n minus 1 divide n. If they divide n, by dividing n means that division will give a remainder of 0. So if that happens, then that I becomes a divisor and is pushed inside that vector. So we are back here. We are here. This is what we are looking at. Generate all subgroups. This is what the main function called for. The main function called for generate all subgroups. So we were here. For D in the divisors, let me again show what it's saying. What it's saying for D in the divisors, it's saying for D inside here, it's saying for D inside this vector, because this vector is the divisors. So this vector here, which was mutable, is what has the divisors. That is what that function is saying for D in the divisors. So the numbers which are there, which we've been pushing into that vector, is what it's referring to. Let's come back and now continue reading. It says, for D in the divisors, see this is a loop, this is a loop. For D in the divisors, then we come inside here. We enter inside this loop. When you come inside this loop, it says, let the generator be n divided by D. That's what we've been doing. That's what we've been doing. So it's saying our n is 24. You see, our n is 24. And then the D inside that vector, we have 1 there, which is a D. We have 2, which is another D there, divisor. We have a 3, another divisor of 24. We have 4, another divisor. We have 6, another divisor. We have 8, another divisor. We have 12. And then we have 24. These are the Ds it's referring to. So it's saying for D in the divisors, for D in these divisors, let's go inside. Let the generator corresponding to that D be n divided by D. So that means the generator corresponding to 1 will be 24 divided by 1. That's what we've been doing in our example above. The generator corresponding to 2 will be 24 out of 2, which is 12. The generator corresponding to 3 will be 24 divided by 3, which is 8. So that's what it's saying. For D in the divisors, let generator be n divided by D. Then it says something else here. Let subgroup generate subgroup. So it's calling for another, it's calling for this function here, it's calling for this function here to generate subgroup for this generator. The generator here, the generator just, for instance, when you talk about generator corresponding to 3 is 8. The generator corresponding to 3 is 24 divided by 3, which is 8. So it's just telling this function that let subgroup equal to, then generate subgroup for n with this generator. Generator is 8 now and 24. So it's telling this one, generate a subgroup for 8. And then it waits. It waits. When this one generates the subgroup, it pushes that subgroup here. So it will wait for this one to generate. It will wait for this to generate. Once this one generates, it pushes it inside that vector. That inside that empty vector, and that empty vector is mutable. So it has done its role. It's now waiting. So now let's see how this one generates. Let's see how this one generates. So this one has been told generate subgroup for n and generator. N and generator. Generator is 8 in this case. We just picked 8. And that's what it's saying. This one is saying generate subgroup n and generator. N and generator. So in our case, it's 24 and 8. Now it begins generating. It begins generating. And you see, once it generates, this one waits and pushes it here. So let us generate it. It begins by letting subgroup creating an empty vector, and you see this hash set. And I didn't talk about it when I was beginning. I was supposed to begin from there. Hash set, because this is a library. The hash set is used to ensure that there are no duplicates. So hash set, you see, once you put inside that hash set, it stores and follows up. Once you generate another subgroup that appears to be one which has already been generated, it detects that. That is why the hash set is there, to ensure that there are no duplicates. That I tried to create without it, and there were duplicates, and so to remove those duplicates, the hash set was to be put there. When just a library by Rust. It's a library by Rust that ensures that there are no duplicates. Now, so let's see how it's generating. There are two things here. The first thing, let mute hash set. I've said what the hash set is. And there's an empty vector. So we'll be pushing them here. The hash set will just be following to ensure that a subgroup that is already inside here is not duplicated. So when we create another one that appears like the one which is there, it's not stored. It's not stored there. Then let current, let mute current. So that means we begin in the current subgroup. The current subgroup, we make it to be 0. Make it 0. Let mute current. Not necessarily subgroup, but let's say, just say let mute current 0. So our current is 0. So let's say our current is 0. Then a loop while, and this loop is very important. This loop is very important, especially when you read this part. While, and you see, you must also read this sign here. This sign, we've made it always, and we said whenever we have this sign, is the same as this, not. No. It's the same as not. The same as not. That sign is the same as not. So let me just read it. Let me just read this so we understand what it is. So it says, while the subgroup is not the current, while the subgroup is not the current. I've just read this part. While the subgroup is not the current, we enter inside here, and then it says subgroup insert the current. So what it's saying is this. Let me just explain. We've created a subgroup. And once this subgroup that we've created is not the current subgroup inside that we've already stored, is not, while it's not the subgroup that is here. If it's not a subgroup that is here, so that is while a subgroup, my internet is unstable. So while the subgroup that we created here is not the current subgroups, is not the current subgroup, insert it inside that vector. That's what it means. Insert that current. Now, then after that, the current was mutable. The current was mutable. So now the new current becomes the old current plus the generator. Then reduce it mod n. Let me show you just a small example. We had 24, our n, and then we had 8 as the generator. So at this part, what we are doing is we mute. So this is just a vector, there's no problem. But the current, our current is 0. Our initial current is 0. And then while the subgroup is not the current, or does not contain the current, yes, so it does not. While the subgroup does not contain the current, insert the current. So our current is 0. So we insert it, insert our 0, we insert our 0 here. So we now have a subgroup there that is 0. And then we update our current. Now our new current becomes the old current plus the generator, which is 8. Then reduce mod. That is 8 reduce mod 24. Again, it will just be 8. So this is our new current. Then is our new current inside here? Is not. So this saying insert it. So we insert. So we had inserted 0. So we now inserted 8. After inserting 8, update the current. So our new current, therefore, is the current, the old current, plus the generator. The answer is 16. Reduce it mod 24. Reduce it mod 24, it remains 16. So Is our new current there? Is not. So again, insert it. Insert the current. Then update the current. Update the current. So our new current now is the old current, which is 16, plus the generator. And this is 24, which is 0, mode 24. Now, then we go back here. Is our current, which is 8, which is 0, inside there? It is. It is, so we don't insert it. So once we find that it's there, because of the hashtag, now hash set, we know that 0 is already there. So we exit. And when you exit with this as a subgroup. Exit with this as a subgroup. And then this one takes over and it pushes it there. Because this is the one that is generating subgroups. Now, so this one is just using the generator. This one is just using the generator to get the subgroup. Then it's just inserting the elements. So this element is just inserting them here. And then it comes up with one subgroup. Then that one subgroup is picked up with this, which then pushes it inside here. Then after pushing it inside there, it asks for another generator. Oh, you see, we had elements. We had elements 1, 2, 3, which were divisors. So again, now it checks about when the divisor is 2. 2 into 24 will be 12. So it asks this. Now find the subgroup when the generator is 12. And this one will repeat the same process and give a generator, give a subgroup. So that is how this code works. And I just want to run it because of time. And then, of course, these notes, explanations, I already have them typed so that you would look at them later on the recording so that you follow. So let me just share. Let me share this. So the code is here. So you can see it begins with the hash set. And of course, I say what that does to just follow up and ensure that there are no duplicates. Now, so it has given us the subgroups. It has given us the trivial subgroup here, then the proper subgroups up to here, and then it has given us the improper subgroup at the bottom. So I told it to arrange those subgroups from this smaller one to the larger one, that order. So these are the subgroups. So that's how it does it. Now, so today we've looked at subgroups of additive group, of course. So we've seen how to get subgroups when for Zn. Then when we meet next, we'll look at how to get subgroups for Zn star. That is a multiplicative group. And also look at how to write the code for the same. Of course, we begin with the manual calculation and then do the code. And the explanations are here. I've said what this hash set does is necessary because the code relies on this hash set to efficiently manage collections of unique elements while generating these subgroups, just to ensure that there are no duplicates. So that's what it does. And this one, I've explained how it gets the devices, And of course, I've also shown by use of an example. That is where I want to stop for today so that next time when we meet, we look at subgroups of Zn star, multiplicative groups. You get these group notes and then look at them later. Thank you.
Thank you.